Hello everyone. In this video, I'll discuss the basics of the CMOS technology. The acronym or short form CMOS stands for Complementary Metal Oxide Semiconductor. In this technology, the basic building blocks or logic gates are designed using two types of MOS transistors, NMOS and PMOS. These two types of transistors complement each other in operation, and this is why this technology is called complementary MOS technology. Let's understand the complementary operation of NMOS and PMOS. First, the NMOS transistor. Here is the simple 2D structure of an NMOS transistor. It consists of N plus dope source and drain regions, P-type bulk or substrate, a gate oxide insulator above the channel, and a polysilicon gate. This is the symbol for NMOS transistor with gate, drain, and source terminals. The NMOS transistor conducts current when the gate voltage is 1. In P transistor, it consists of a P plus doped source and drain regions, N-type substrate, gate oxide insulator, and a polysilicon gate. This is the symbol for P transistor. In operation, the PMOS turns on or conducts current when the gate voltage is 0. In operation, the NMOS and PMOS transistors work like a switch. As shown in the switch model over here, when the gate voltage in NMOS is low, the switch is open and there is no current between drain and source. But when the gate voltage is logic 1 or high, the drain terminal is connected to source. The switch is closed, allowing current to flow. On contrary, the PMOS switch is closed when the gate voltage is low or logic 0, otherwise it's open. After understanding the switch model for PMOS and NMOS, now let's look at a simple CMOS circuit designed using one NMOS and one PMOS, the CMOS inverter. This is the schematic. In this circuit, the gates of the PMOS and NMOS are connected to form the input port labeled here as A. The drains of the PMOS and NMOS are connected to form output port labeled as B. The source of the PMOS transistor is connected to supply voltage VDD, and the source of NMOS transistor is connected to ground. If we summarize the functionality of this inverter circuit, it is when input A is 0, output B is 1, and when input A is 1, output B is 0. This behavior can be expressed as a Boolean expression as B equals to A bar or not of A. This is the logic gate symbol for a CMOS inverter. Now let's look at the switch model for the CMOS inverter to understand the behavior. When the voltage at input A is 0, the PMOS switch is closed and NMOS switch is open. Since the PMOS switch is closed, the output node B is pulled up to VDD or logic 1 by PMOS. When the voltage at A is 1, the NMOS switch is closed and PMOS is open. The output voltage at node B is pulled down to ground or logic 0 by NMOS. The inverter circuit we discussed so far consists of a single PMOS transistor for pulling the output up and a single NMOS transistor for pulling the output down. However, more complex designs can be built by combining multiple PMOS and NMOS transistors for pull-up and pull-down networks, respectively. The PMOS and NMOS transistors can be connected either in series or in parallel. Depending on the configuration, whether they are in series or parallel, the overall pull-up and pull-down strength of the circuit changes. First, let's see the NMOS. When two NMOS transistors are connected in series, as shown here, the node X and Y are connected only when both A and B are 1. This configuration implements AND logic. When two NMOS transistors are connected in parallel, as shown over here, nodes X and Y are connected when either of the inputs A or B is 1. This configuration implements OR logic. Similarly, for PMOS, as shown here, when two PMOS transistors are put in series, nodes X and Y, as shown over here, are short-circuited, but only when A and B both are 0. And when transistors are connected in parallel, nodes X and Y are connected when either of the inputs A or B is 0. Now let's look at a slightly more complex circuit, a two-input NAND gate. In this circuit, the output X is connected to VDD when either of the inputs A or B is 0, and the output X is connected to ground when both A and B are 1. Now let's understand the pull-up and pull-down network in two-input NAND gate. The PMOS section or the pull-up network is highlighted in blue. The pull-up network connects output node X to VDD when either A or B is 0. The NMOS section or the pull-down network is highlighted in pink, which connects node X to ground when both A and B are 1. The pull-up and the pull-down networks are designed as conductive complements of each other, ensuring that when one is on, the other one is off. This complementary operation achieves the desired NAND operation. This is how we can put together the schematic of a generic CMOS gate consisting of a pull-up network and a pull-down network. The pull-up network is made of PMOS transistors and the pull-down network is made of NMOS transistor. Now let's work through an example where we take a Boolean expression and design it in CMOS technology. Suppose we want to design a Boolean expression O equals to A or B and C whole bar. Using De Morgan's theorem, we can rewrite this expression as A or B whole bar ORed with C bar. Further rearranging gives us A bar and B bar ORed with C bar. First, we design the pull-up network. In the pull-up network, the output O is pulled to logic 1 when A bar and B bar are 1. So let's connect two PMOS transistors in series with gates driven by A and B. The output O can be also pulled to VDD when C bar is 1 or C is 0. So let's place another PMOS transistor in parallel with the series connection with its gate driven by C. This makes the whole pull-up network for this Boolean expression. The pull-down network is the complement of the pull-up network. The PMOS transistor connected in series in pull-up are replaced by parallel NMOS transistors. The PMOS transistor in parallel in pull-up network is replaced with an NMOS transistor in series with the parallel NMOS transistors. And this is the pull-down network for the circuit. By designing the pull-up and pull-down networks in this way, we make sure the complementary behavior is achieved in the CMOS gate. This is all for this video. Hope this helps you to understand complementary behavior of NMOS and PMOS in CMOS technology.